Inside your computer, hidden within a silent metal box, lies one of the most mechanically complex devices ever mass-produced by humanity, the hard disk drive. To the naked eye, it looks like a simple spinning disk. But look closer. Beneath that aluminum shell, components move at speeds and tolerances that would make a Formula One engine look like a child's toy. Imagine a commercial airliner flying at 500 miles per hour, just a fraction of an inch off the ground, while counting every single blade of grass along the way. That is the daily life of a hard drive. It is a masterpiece of physics, material science, and mechanical engineering. Every time you save a photo or load a game, thousands of parts work in absolute unison with zero tolerance for error. A single speck of dust, thinner than a human hair, would be like a mountain to the sensitive components inside. Today, we go beyond the casing to explore the brutal engineering required to turn raw metals and glass into a digital vault capable of storing trillions of bits of information. Born from the earth and forged in clean rooms cleaner than a surgical theater, this is the story of how sand, aluminum, and magnetism became the memory of our world. The heart of the drive is the platter. While older drives used aluminum, modern high-capacity disks use a specialized glass and ceramic substrate. Why glass? Because at 7,200 revolutions per minute, any imperfection causes catastrophic vibrations. These platters must be perfectly flat, within a few nanometers across their entire surface. If a platter were scaled up to the size of a football field, the largest bump on its surface would be no taller than a single blade of grass. The manufacturing begins by casting these glass discs, and then subjecting them to a series of chemical baths and mechanical polishing stages. They are diamond ground to achieve a mirror-like finish that is fundamentally smoother than any mirror in your home. This smoothness is critical because the read-write head will eventually fly over this surface at a height smaller than the thickness of a fingerprint. Once polished, the glass is chemically strengthened through an ion exchange process, ensuring it can withstand the immense centrifugal forces of high-speed rotation without shattering. This is the blank canvas of our digital world, but it's still just glass. To store data, it needs something more: magnetism. To make the glass platter magnetic, it undergoes a process called sputtering inside a vacuum chamber. This is where the physics gets truly exotic. In a series of automated chambers, the platters are bombarded with atoms of specialized alloys, including cobalt, chromium, and platinum. But they aren't just sprayed on. They are deposited in a very specific layer cake structure, sometimes over 10 layers deep. Each layer is only a few atoms thick. The most critical layer is the magnetic recording layer, which consists of billions of microscopic magnetic grains. These grains are incredibly small, only about 10 nanometers in diameter. For perspective, you could fit over 10,000 of these grains across the width of a human hair. The engineering challenge is to keep these grains stable. If they are too small, their magnetism can flip spontaneously due to room temperature heat, a phenomenon known as the super-paramagnetic effect. To fight this, engineers add a layer of ruthenium, an exotic metal that helps hold the magnetic bits in place using quantum mechanics. Finally, a protective carbon overcoat, as hard as a diamond, and a microscopic layer of lubricant are applied. The platter is now ready to hold the weight of your digital life. If the platter is the canvas, the read-write head is the needle, but it never actually touches the record. The head is located on a component called the slider. The bottom of this slider isn't flat, it's etched with a complex pattern of grooves and ridges called an air-bearing surface. As the platter spins at thousands of rotations per minute, it creates a cushion of air, a literal windstorm inside the drive. The slider uses this wind to generate lift, just like a jet wing, allowing it to hover exactly 5 nanometers above the surface. If even a single particle of smoke, which is about 250 nanometers wide, gets in the way, it's like a plane hitting a skyscraper. This head crash would destroy the data instantly. Modern heads utilize tunneling magnetoresistance, or TMR, to sense incredibly faint magnetic fields. Some of the most advanced drives even use heat-assisted magnetic recording, or HAMR. These heads contain a tiny laser that heats a specific spot on the platter to 450 degrees Celsius for just a billionth of a second to make it easier to write data. This happens millions of times per second as the head zips across the disk. How does the head find the right piece of data in just milliseconds? It uses a mechanism called a voice coil motor, or VCM. This is the same technology found in high-end audio speakers, but engineered for extreme precision. A coil of fine copper wire is attached to the back of the actuator arm, suspended between two incredibly powerful neodymium magnets. When the drive's controller sends a burst of electricity through the coil, it creates an electromagnetic field that reacts with the permanent magnets, snapping the arm into position. We aren't just moving the arm, we are moving it with terrifying speed. It can accelerate from 0 to 60 miles per hour in a fraction of a second, then stop instantly on a track that is only 30 nanometers wide. This requires massive amounts of force, yet it must be controlled with the delicacy of a jeweler. To compensate for vibrations, many modern drives use a dual-stage actuator. A secondary, microscopic motor made of piezoelectric material is placed right at the tip of the head, allowing for sub-nanometer adjustments. It is a constant battle against physics to keep the head aligned while the world around it vibrates. To keep the air cushion stable, the platters must spin at a perfectly constant speed. This is the job of the spindle motor. In high-performance drives, this motor spins the disks at 7,200 revolutions per minute, or RPM. At this speed, the edge of the disk is traveling at over 70 miles per hour. But traditional ball bearings aren't quiet or stable enough for this task. Instead, engineers use fluid dynamic bearings, or FDB. The motor shaft is supported by a microscopic film of specialized synthetic oil. This oil dampens vibrations and prevents metal-on-metal contact, allowing the drive to run for years without wear. The motor itself is a brushless DC motor containing a series of copper coils that are pulsed in sequence by the drive's electronics. The timing must be perfect. Any variation in speed would cause the data tracks to drift, leading to read errors. This motor is the silent workhorse, maintaining a steady heartbeat that allows the rest of the symphony to play. It's a delicate balance of fluid dynamics and electrical engineering, designed to spin billions of times over the life of the drive without ever failing. In the quest for higher capacity, engineers hit a wall: air. At high speeds, air is thick and turbulent. It causes the platters to wobble and generates heat through friction. The solution? Replace the air with helium. Helium is 1/7 the density of air. By sealing the drive and filling it with this noble gas, internal turbulence is reduced by 90%. This allows engineers to pack the plotters closer together, increasing the number of disks inside a single drive from 5 to 10 or more. It also reduces the power needed to spin the motor by nearly 30% because there is less gas drag. However, helium is a notorious escape artist. Its atoms are so small they can leak through solid metal or plastic over time. To solve this, the drive's outer casing is laser welded shut with a hermetic seal. This creates a permanent, pressurized environment where the components can operate in a near frictionless state. It is a vacuum-tight tomb for data, engineered to stay sealed for a decade or more, even as the world around it changes. None of this mechanical wizardry matters without a brain to control it. Attached to the bottom of every hard drive is a printed circuit board, or PCB, containing the drive controller. This is a specialized microprocessor that acts as the conductor of the orchestra. It manages the error correction code, or ECC. Because data bits are so small, they are occasionally misread due to magnetic noise. The controller uses complex math to reconstruct the original data on the fly, instantly. It also manages the servo system. On the platters, between the data, are servo tracks, hidden markers that tell the controller exactly where the head is located. The controller reads these markers hundreds of times every single second, making tiny electrical adjustments to the voice coil motor to keep the head perfectly centered. It also manages localized caching using high-speed RAM chips, ensuring that data flow between your computer and the spinning disks is as smooth as possible. It is a high-speed translator, converting the language of electricity into the language of magnetism and back again. The final assembly of a hard drive cannot happen in a normal factory. It must take place in a Class 100 cleanroom, or better. In these environments, there are fewer than 100 particles of dust per cubic foot of air. For comparison, the air you are breathing right now contains millions. The assembly is performed almost entirely by high-speed robots. Human presence is a risk. A single flake of skin or a strand of hair would be a death sentence for the drive. The base casting, usually made of die-cast aluminum, is cleaned in ultrasonic baths before entering the line. The spindle motor is pressed in, the plotters are stacked with precision spacers, and the actuator arm is delicately lowered into place. Once the internal components are secured, the top cover is screwed down with a gasket seal. In the case of helium drives, the air is evacuated, replaced with helium, and then the final metal seal is laser welded. From this point on, the internal environment is isolated from the rest of the planet, a pristine world where the laws of physics are exploited to store your most precious memories. Before a drive leaves the factory, it must prove its worth. Every single drive undergoes a burn-in process that can last from 24 to over 100 hours. The drives are placed in massive racks where they are subjected to extreme temperature cycles, from freezing cold to blistering heat, while performing constant read and write operations. The controller tracks every single error. If a drive has too many bad sectors, microscopic flaws on the plotter, it is rejected or its capacity is downrated. During this phase, the drive also maps its own unique map of defects, learning which parts of the disk to avoid. Only after passing these brutal stress tests is the drive cleared for shipment. It is a testament to modern manufacturing that we can take millions of these incredibly fragile, nanoscale components, mass-produce them at a low cost, and have them work reliably for years on end. The hard drive is more than just a storage device. It is a mechanical marvel, a bridge between the physical world of spinning metal and the digital world of infinite information. Your data is safe, held in place by the most precise machine ever built. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.